All right. So get started here. Pick up where we left off. Don't know if we'll get to kind of work on some Excel stuff today, but that is coming up for sure on Monday. I believe what's due at the end of the day today, that Connect assignment. So if you haven't done that already, make sure you get that done by the end of the day. It's set so that it auto submits. So, you know, you're working on it and you don't hit submit, don't worry, whatever work you had kind of saved on there, it will automatically submit that. You'll see the next one pop up there after tonight. Sometime tomorrow, I'll make sure I get that one up there. You can start working on that one. We'll have covered a little bit of the material. You know, you can kind of start working on the problems there. And then probably after class Monday, I'll assign an Excel assignment. So those two assignments will be due prior to our first exam. I also will have more information on this next week, but I'll probably be pushing the exam date up at least one class period. I may have to maybe missing a class period. I'm not 100% sure yet. So I'll have more information on that on Monday, but we won't be missing any classes next week. It might be the following week. So I'll make sure, you know, I have more information about my schedule. I'll make sure that I kind of translate that to you guys next week. Yeah.
So you're gonna be like a study guide or something?
Yeah, so I'll get up some practice exams. In fact, I should be able to get those up sometime tomorrow. I don't a lot of the stuff we haven't covered yet, but you know, if you're wanting to kind of have some more problems that over the material we've already covered, you know, the first however many, you know, half of the questions would be stuff probably that we've already covered up to this point. Yeah. Yep.
Yeah, I've been using the check my work option on the homework.
You should.
care. Okay.
No,
sure you
it's there. Yeah.
Click it.
Yeah, I mean, you'll notice like I don't give you a lot of multiple choice questions because obviously it wouldn't be very easy, you know, pretty easy. Now there might be a few on there, so you can get the correct answer pretty easily, but I'd make sure, you know, you understand why the correct answer is what it is. When we're guessing numbers, right? You can sit there all day and guess an infinite number of possible numbers. So I'm not too, you know, if you want to take the time to do that, by all means, go ahead. But yeah, be using that tool. Try to get as many points possible there on that Connect homework. Any other questions before we hop into things today? All right, so we left off. I think I had maybe, you know, we talked about some kind of basic notation, some intersections, unions. I think maybe show you these Venn diagrams, kind of how to think about this. We then said we want to start being able to interpret these contingency tables. Right? So this is kind of a quick review of how we read these, and then we'll really see their usefulness today. So these total columns represent the probability of whatever the event the row or column heading is. So for instance, we wanted the probability of A, we went over to the total column. I kind of did a little bit of an insight as to why you can reproduce those totals if you add across the rows or if you add down the columns. So even if I left these total columns off, we should be able to add across the rows or down the columns to reproduce those. Okay. The intersections we said were all representing those top four left cells, right? So the probability of B and A complement would have been 0.1 here. So, or probability of A and B was 0.4. We could look at the intersection of the two complements, right? Just depends on what we're looking for the intersection of. So that's kind of where we left off, if I recall correctly. Now we'll go over some probability laws. This one, it's not super interesting or that complicated, but it doesn't matter what order we say things in, right? So basically, if I think about event A and event B, maybe it's the probability that I make more than $50,000 and I'm over 6 foot tall. Well, it's the same thing as saying that I'm over 6 foot tall or I make more than $50,000. Right? It doesn't matter which order I say that in. I'm talking about the same union, right? I could say, what are all the outcomes that are in circle A or circle B? The same thing as saying, what are all the outcomes that are in circle B or circle A? The ordering doesn't matter there. Same kind of thing with the intersection. It doesn't matter if I say what's the probability I'm in both A and B, or what's the probability I'm in both B and A. Right? So when it comes to the union and the intersection, the order doesn't matter. Okay. So that one's pretty easy. I don't think that will trip anybody up. So I had a gradient, right? So when you say it's fine, it's actually fine, there's very little overlap, the intersection is relatively small there. We'll kind of talk about some more rules and maybe what happens if there is no intersection. So I've got the complement rule up here, and I'll kind of provide a little bit more insight. Let me make a little bit more sense of this. So if I'm thinking about everything that's in that circle A, right? Everything that's in this event A that I've defined. Okay? Well, we can think about A as maybe being an event of I make more than $50,000. Okay? So if I take the probability of A and I add everything outside of that, or the probability of A complement, well, if I think about it, what's the probability that somebody makes greater than 50,000? Adds that, the probability they make 50,000 or less. Well, that covers every possible income value. So these should just add up to 1. Right? And then if I rearrange this a little bit, I can always find the complement. If I subtract this from both sides. And that's kind of where that complement rule comes from, right? So anytime I tell you the probability of an event, you know its complement is just 1 minus that. Right? And this is by definition that the complement is everything outside of it, every possible outcome that's not in A. So we know this should include every outcome, and we know the probability of every possible outcome, those should always add up to 1. But visually, it's kind of nice, right? We have this rectangle. It kind of represents every possible outcome. So we know that area is like 1. And then it kind of has 2 components, everything that's in circle A there and everything not. So I don't think that's too bad. A little bit tougher might be the addition rule. Right? So if we want the union of 2 events, we might initially think I can just add the probability of each event, right? What's the probability of M and A? Or, probability of M and B. The problem is you kind of, the visual is nice here because you can see that if I take everything that's in circle B and I add that to everything that's in circle A, what I've done is I've double counted what's in the middle. So if I add the probability of both events, how can I make sure that I didn't double count it? Well, if I double counted it, I'll subtract it out 1 time, right? So we take the probability of each event, add them together, and subtract out what we double counted, with what was in both of them. We should just be left with the probability of the union, right? Or just kind of remember the union was this U sign, which we can think about also, we usually read this as A or B. Okay. Any questions here? I'll break this down a little bit differently. Here's another way of thinking about it. I don't have a visual here. So if I've got circle A, circle B here. What would this area represent? If I want to break the union down into 3 components, well, I can think about this circle is going to be everything that's in A, but not in circle B. So I could take the entire circle of A, and then if I subtract out the intersection, I'd be left with just this like crescent. Right? And then if I wanted to get this area, well, that's circle B, but take out the part of circle B that's also in A, right? I'd be left with just what's in between here. Well, and then how do I get the rest of the union? Well, what's in the middle here? I would just add that intersection back in. So it's just another way of thinking about coming up with this area. Now, if you notice here, I'm adding and subtracting the same thing. These will cancel. And sure enough, I'm left with the exact same thing I had up there, which was the union of these 2 events, right? What's in both circle A or B is the probability of each event added together. And then you subtract out that intersection. Or you can think of it as I'm subtracting out what I'm double counting. Now, you don't have to go through those steps every single time. That's just another way of thinking about it. Right? So I think that's what I have on this slide. We could rewrite this in a slightly different way. You can see things cancel, and we're left with our same addition rule. Right? But I want to find the probability of the union of 2 events, the or A or B. It's just take the probability of each event, add them together, and subtract out that intersection. Questions up to this point, because I'm going to make it a little bit more complicated here in a second. All right, so. I want to show you two ways of doing this. I can't remember what one I did it in, but I'll tell you the first one. I think I'm gonna skip ahead here. There we go. So one way you can find a union, and I think this is definitely the less technical way, but it works. And if it's easier to remember, then that's fine. Okay. So if I want to find the union of two events on my contingency table, well, these top four left cells only told me the intersections. Right? But if I want the union, I can go to the intersection of two events, make like an L, add these up, and it should give me the union. So in this case, right? Sorry. In this case, if I add these up, I get what? 0.2 plus 0.4 plus 0.1 is 0.7. So if I use this not very technical method, right, where to find the union, I go to the intersection, make an L, and then add those up, I'll get about 0.7. Right? But we just said another way of writing the union of two events is take the probability of each event and then subtract out what we double count, which is the intersection. Well, I can find all three of these components on my contingency table, right? What's the probability of A? I want the probability of A. Go over the total. That's just 0.6. What's the probability of B? Go down to the total, 0.5. What's the probability of the intersection? Intersection of A and B is 0.4. If I add these up, I end up getting 1.1 minus 0.4 or 0.7, which was the exact same thing if we use the less technical way, right? So you can kind of think about here, I could also find this using the actual definition of how we find the union. This is probably the better way to find it, just to kind of help instill what that addition rule actually is. But to find the union, I want to find the probability of each event and subtract out what was involved. But if I want to use the less technical method of creating that L, I can do that as well. Any questions on this before we keep moving? So, one definition we can think of that makes our life a little bit easier, and sometimes we'll start using this term, right? Because sometimes we want to guarantee that this is the case. So we say that two events are mutually exclusive if they can't happen at the same time, right? This would be something like, what's the probability somebody makes less than 20,000 and they make more than $100,000 in income? Well, there's no possible income value that meets both those criteria. So the intersection of those two events, we would say, is can't happen. The probability of the intersection of those two events should be 0. So what would that look like in a contingency table? The intersection of the events would have a 0 probability there. Not a very interesting example, but it can occur, right? It also makes finding the union of the two events really easy because we're not double counting anything anymore, right? There is no intersection. So if we have mutually exclusive events, to find the union, we can just add up the probability of each event. Visually, what does this look like? Well, if the intersection doesn't exist, there will be two circles that don't overlap, right? So all of these things are just saying, these two events can't occur at the same time. They're mutually exclusive. The probability of that intersection is equal to 0. Pretty easy definition. It's not too bad, right? So being mutually exclusive kind of makes our addition rule a little bit easier. Internet access, phone internet access in the 90s was mutually exclusive, right? You had one phone line, you either could be on the internet or you could be on the phone at the same time. You couldn't be doing both. This got me in a lot of trouble when I was in high school. So you guys probably didn't have to deal with this. I don't know, but so we can take this one step further, which is I can use this addition rule, and I'll try to give you. So for right now, I'm telling you this shaded blue area is the intersection of the complements. So I'll give you a little bit of a visual, but also an intuitive reason why that is the way it is, instead of just kind of telling that. So if I think about, actually, I want multiple colors here. So I'm gonna use these. So let's think about. Here's my event A. What would this shaded black area represent? A complement, right? Everything that's not in it. What if I have then circle B? Everything outside of circle B is B complement. Where this shaded black and green area overlap is going to be only areas that are not in either one of those circles. Right? So that's why everything outside of those circles, what we're really saying is it's the intersection of A and B complement, right? So this blue shade area represents the probability of intersection of those two complements. You can kind of think about it intuitively that everything in that white space, everything that's in either A or it's in B, or the area outside of that will be everything that's not in circle A and also not in circle B. So everything that's in circle A or B, that's the union of these two events. Everything that's not in those circles, everything that's not in A and also not in B, well, that literally is A and not in A, not in B is the intersection of the complements of those two events. But we want to kind of create this shader, you kind of see where they overlap, A complement and B complement would be this area outside of either circle. So it's a little bit of reason as to why that's the intersection of the complements. I'm not going to necessarily make you reproduce that, right? What I might have you do is think about it in a slightly different way. Okay? So everything that's in that white space, that's in circle A or B, it's like a goofy U there, is the union of those two events, right? Well, if I then add to that the blue shaded area, which is the intersection of my complements, that fills up the entire experimental outcome space, which this rectangle, which always kind of has an area of 1, represents every single possible outcome. If I add up the probability of every possible outcome, that should always add up to 1. So I know those two components add up to 1. Well, here we can use our addition rule because I know that I can rewrite the union of two events as the sum of the probability of each event, subtract out what I double counted, which was the intersection, and then we still have this intersection of the complements. We're not really substituting anything in there. And that's where I'm coming up with this. So a lot of the times we'll have this information, right? You can imagine from a contingency table, well, usually we have like the intersection of the complements on there. We have the intersection of two events. So these are going to be things I can do even with my contingency table. So we'll walk through an example together. So I've got this equation up here. I've got kind of 4 pieces of information. So what if I know 3 of them and I'm looking for a 4th, right? So here I want to find the probability of B. So how can I do that? Well, I know that if I use that addition rule to substitute in, so I'm just rewriting what I had over there, but I'm going to put it on one line, so hopefully it's a little bit easier to kind of follow. Here I'm told the probability of A is 0.5. I don't know the probability of B, right? That's what I'm looking for. Question mark. And then the intersection I've got is what? 0.1. And then the intersection of the complements, I was also told was 0.3. Well, at this point, I have one equation, one thing I'm solving for. If you want to think about this like in a math, this is X, right? I'm trying to solve for this one missing piece I don't know. Oh, this is pretty basic algebra, right? So 0.5 minus 0.1 is 0.4, plus 0.3 is 0.7. So I'll subtract 0.7 from both sides. That cancels out. Subtract the 0.7 here. And I'm left with that thing I didn't know is equal to 0.3. Okay. It's really, once I write this equation out, plug in what I was given, it's a matter of kind of algebra. Okay? I have to be given at least 3 of those components, otherwise I can't solve for the other 2. But as long as I have 3 of, or sorry, I have to have at least 3 to solve for the 1 I don't know. If I was only given like 2, I can't solve for the 2 that I don't know. But it should be pretty straightforward. Any questions here before we keep moving? Now, one thing I would say is don't get lost in the visual too much, because the probability of A represents this entire circle, not just the shaded white area, it's the entire event circle A. And the probability of B that we're looking for represents the entire event circle of B, right? Not just that kind of dark blue area. So that's basically what I had up here on the board. I want to see if you guys, and of course I forgot to, I thought I had it started up, but apparently I didn't, so. Give you guys a little bit of time, kind of talk to the people around you. Pull this up. As we wait for it. Oh, that's not it. All right, where are we at? So we're right here. Okay. There we go. So I want to kind of see where we're at with things. Just work through this one. Oop. So I want you guys to work through this. Okay, so I'm giving you some different values. We're going to have to find different missing components. So here, I'm telling you the probability of A and the probability of B. I'm giving you the probability of the intersection of the complement. But what I want you to find is the probability of that intersection. Okay. So I'll give you guys a couple minutes, talk to the people around you, kind of work together. You shouldn't have to be super quiet during this. I want you to kind of work with each other. Maybe you know something the person next to you around you doesn't know. Maybe they know something you don't know. So I'll give you a couple minutes to work on this and then we'll talk about it. It should be very similar to the one that we just worked through. We were just looking for a different missing component here. Said even if you don't want to work with others, check with the people around you, make sure you're both getting right and not too concerned about you guys having.
Question about the class. Will it mostly be like problem solving, or is it gonna be like definitions as well? Like,
Mostly problem solving.
Okay.
Yeah. Like the terminologies, the definitions, you should really only need to know so that you can understand the words that are, yeah, it's not, no, I'm not gonna ask you for like what's the definition of
Okay,
it?
okay.
Yep.
Alright.
Yeah, I'll get those practice problems up tomorrow too, and those should be a pretty good indicator of the types of problems you'll see.
I also have a question. On campus, I haven't been getting the credit for.
Okay, I'll mention that here. So probably need to go on your Clicker account and register the remote on there as well. And so I put up an announcement on Canvas that should have links that would help direct you there to do that, or like have the steps. But have you created an iClicker account?
Maybe.
Okay.
I think
So if you have, then you need to log on to that. And then under your profile, there'll be an option to register remotes, and you have to register it there as well.
Okay.
So I probably have you. It looks like I think everyone has joined the class. But some of you, the remote isn't registered yet. So I see your name or I just see the remote number.
Okay.
Once you register that remote, then it should link it up to the
Okay.
board. Yep. And you can check with me after class. I can kind of help show you how to do it.
I think I heard you say something about.
Yeah.
last time. I looked before class and I couldn't find. it.
Yeah, I'll say something at the end of the class. All right. If you haven't gotten a guess in, take your best, or haven't gotten an answer, and take your best guess now. I think there was 16 of us earlier, so hopefully I counted correctly. Close this out here. All right, so this should be as simple as what we just did here. We're just gonna have different components, right? So I'm starting out with the same equation. It's just now, the probability of A is what? 0.3. The probability of B is also 0.3. Now here, I'm looking for the intersection, so I don't know what that is yet. And the intersection of my complements is 0.5. Okay. Now, if you're not careful with your algebra here, you might make a very easy mistake, although I didn't even give it to you as a possible answer. But here, if I have 0.5 plus 0.3 plus 0.3, that's what? 1.1. So I'll subtract 1.1 from this side and cancel that out. I subtract 1.1 here. And I might think, oh, okay, my probability is -1. But remember, there's a negative sign in front of here, right? And we can't have negative probabilities. The lowest the probability could ever be is 0. So you have to remember, oh, I've got negative signs on both of these. If I divide by, I don't know, -1, that cancels out the negative sign on both sides, right? So I'm left with just the intersection of the two events is equal to 0.1. So when I'm solving for the intersection, it's going to be a little bit trickier. So I have to remember that I've got this negative sign up front. Now, what I could have also done, I'll, just move my probability to the other side, right? Add it to both sides, and then subtracted 1 from both sides. And then that way I don't have to worry about that negative sign. But, there's multiple kind of ways to do this algebraically. Yeah.
For the intersection, it's a constant thing, it'll always be negative, right? You're trying to find subtracting it from everything else.
Yep. So, right. And the reason why we start out with this equation where we're subtracting the intersection, I think I already, is because really what we're doing is saying, look, the union of two events plus the intersection of their complements, these add up to 1. I'm just going to rewrite the union using that addition rule, right? That addition rule was take the probability of each event, subtract out that intersection, which is what we double count. So yeah, you'll always be subtracting that intersection of the two events there. Any other questions on that? Okay with that? So everybody got it right? I check. All right, so I would expect you to be able to kind of solve one of these. Going into the UK. So no questions before we move on? Now's your time to ask them. So the next law we're going to talk about, I think, is a little bit trickier. I'll try to give you some examples though, maybe to intuitively kind of help make a little more sense of it. So the multiplication rule, I'm going to start out kind of just telling it to you, but then I'm going to give you what I think is a better explanation as to why it is what it is. So we talked a little bit last class about conditional probability. So we remember what I said was whatever's on the right-hand side of that vertical line, it's essentially like we're saying we know that this has occurred, right? Given that this has already happened, right? So given that A has already happened, what's the probability I see B occur? Okay. So what we're going to call this, if I were to write a conditional probability, I'm thinking of this as this is the conditional probability of event A. Okay. I'm conditioning on that B has already occurred, but I'm still looking for the probability of A. All right. So remember, the way we would read this is A given B, or given that B has already occurred, what's the probability that I now see A occur? So we would call this the conditional probability of A. We want the probability of A, but conditioning on something else already occurring. When we just have the probability of A, we'll call that the unconditional probability I guess if I'm being complete here, of A. Okay. So if I'm looking for the intersection of two events, what ends up being true is I can just take the conditional probability of one of those events, multiply by the probability of whatever I'm conditioning on, and those things should be equal, right? So if I take that conditional probability times the probability of whatever I'm conditioning on, that should give me the intersection. So why does that work? Or, sorry, I'm gonna then rearrange this equation a little bit so that I can have a better, so I can then give you a better understanding of why this works, okay? So all I'm gonna do here is rearrange this equation a little bit. So I'm gonna divide both sides by the probability of A. So then I can solve for my conditional probability. So if I do that, I would have two equations that look like this. So I'm no longer solving for the intersection of the two events. I'm now solving for just that conditional probability. So why does this end up holding? Okay. So this is where I think I can give you a visual that makes a little bit more sense of this. So let's go with, and it's like I'll do like a really extreme example just to prove the point. So let's say I have my entire experimental outcome space here. What's the area of this rectangle of the entire experimental outcome space? 1. Then let's say this entire space here, right? And I can actually, all of this is event A, okay? I tried to draw this visually so that you could guess, but if I exactly splits this in half, what would the probability of A be? 0.5, right? I'm then going to think about, okay, what if I also had, let me see if I can get this to, kind of that area split in half, so that I've got the probability of B would be what? Yeah, 0.25. Okay. So my unconditional probability of B is 0.25, right? But what if I want the conditional probability of B? Well, I have an equation that should work up there, but here I'll try to show you why that equation holds. If I tell you that A has occurred, right? What's the remaining space of experimental outcomes left? None of that. If I tell you, given that A has occurred, I know that the outcome is somewhere over here, somewhere in this new space of 0.5. So by conditioning another event, essentially what I've done is I've changed my denominator, which used to be 1, so I didn't even see it there. Really, I could almost ignore it. It's now limited down to whatever this new space is. In this case, 0.5. And then of that remaining space, how much of it is event B? Well, 0.25, right? I had, the area of B here is 0.25. So once you tell me that A has occurred, I know that half of these outcomes are in event B as well. So knowing that A has occurred, right, or given that A has occurred, the probability of B has now increased up to 0.5, right? By knowing that A has occurred, I know it's much more likely that I see an outcome in event B. Because before, if you just wanted the probability of B, I had this entire space and there was only a fourth of it. That was the probability, in event B. Now, of the remaining space, half of it is in event B. So by conditioning on these other events, essentially you're changing the denominator. Well, notice, what was that area of 0.5? Well, that was really just the probability of A, right? My remaining space. And then what was the likelihood that if I'm in A, I'm also in B, or the probability that I'm in A and in B, which is exactly what we have up here, right? We can rewrite conditional probabilities as the intersection of the two events, but then the denominator will be, well, what's the new space? What have we conditioned on? That's why we divide by the probability of whatever we conditioned on. Okay. This kind of gives me a nice example. Like it makes, the conditional probability is going to be much larger, right? Once I know that A is also, once I'm given the fact that A has occurred. Let me give you one more example of this. Just to think about conditional probabilities in a different way. Let's say it's something like this. So that one's pretty good, but I can go even more extreme and I'll use kind of circles here. So let's say, here's circle A. Okay. Oh, no, that's not what I want to do. Might be hard for you guys to see, but I think it'll make the point better. So let's say I've got circle A here, right? It's pretty small. I don't know. Let's say that 0.1. And then let's say I've got circle B here as well. And the probability that I'm in circle B is also common, right? They're relatively small. And then I tried to draw this to be perfect. I probably could have used rectangles to maybe make this a little bit easier. So, you know, if I had done something like this, right, so that they exactly kind of split each other in half. What I hope the visual kind of shows is that the intersection of those two things is going to be half of each circle. So the probability that I'm in that intersection is going to be kind of 0.05, right? Half of each of them. You kind of think about it as here. If this had a space of 0.1, this had a space of 0.1. What's in the middle here? 0.05. That way 0.05 plus 0.05 gives me 0.1, 0.05 plus 0.05 gives me 0.1. So if I just wanted the probability, the unconditional probability of A or B, it's going to be pretty small, 0.1, right? 10% chance. But as soon as I give you some additional information, so given that I know I'm somewhere in circle B, now what's the probability that I see A? Well, my new area, right, the remaining space I'm now left with is 0.1, right? So I can kind of think about it as my new denominator is 0.1. Well, really, what was my new denominator? That was just, I wish I had more board space here. Well, that's really just the probability of B, or the probability of what I'm conditioning on. I then think about, okay, of that remaining area, how much of it is also in A? We kind of said that overlap, that probability was 0.05, or that area was 0.05, which really just reflected the intersection of those two events. So it doesn't matter if I start out kind of using that definition and then plug my values of 0.1 or 0.05 in, or if I was just plugging that in, thinking about kind of visually what that space would look like. But here, you know, now what's the conditional probability of A, right? Once I have this additional piece of information, well, it's went all the way from 0.1 all the way up to 0.5. So sometimes having some additional information can really increase, you know, the probability that you know an event occurs, right? I think the example I gave last class was like, you know, the probability of ball getting out of my car dramatically increases if you then give me the additional information that event B has occurred, which is that it's been flowing in rain for the last hour. Okay? So, but you know, this is kind of what it looks like with some actual numbers and not just this kind of toy examples.
Questions on this before you keep moving?
Yeah.
Say like on there, you did 0.1 for both. If say they weren't exactly equal, will they be equal? Or
They don't have to be.
okay, so how would you calculate it? Because you said it's half.
Same way, right? So let's say try to draw it in the same place, right? So let's say that circle A, or that event A occurring, is much more likely. So circle A is much larger, but right, it still has the same overlap with circle B. So the intersection of these two is still the same amount. We still calculate it the same way. It's just now, you know, you can notice once I know that B has occurred, right? Well, there's still only a 0.05 likelihood of them also in A. So it doesn't matter if these values aren't the same. What matters is whatever I'm conditioning on, that's like my new possible area. It's no longer one. It's going to be something much, much smaller.
So you're gonna have the smallest number. Is that what you're saying? Like, because you said that PA and B is 0.05 because it's half the.
Yeah, so I was doing that before just to kind of make the visual a little bit easier. You would have to be told what this probability is, right? You would have to be given this piece of information that you know what the intersection is. Yep, yep. Yeah, and you'll notice, so when the numbers were the same, it didn't matter which way I was looking, if I was looking for the conditional probability there or the conditional probability. Notice now, if I wanted to find instead the conditional probability B, well, notice that doesn't really change a whole lot because if I know that A has occurred, well, I've now got a remaining space of 0.5, right? So I can kind of think about it as my denominator is 0.5. The intersection is still 0.05. So the conditional probability here ends up actually being the exact same as the probability of the event itself, right? This additional piece of information didn't matter, right? Because before, of the entire space of 1, 0.1 of it was in B. Now of the remaining space of 0.5, 0.05 of it is in B. Well, 0.05 out of 0.5 ends up being that same probability. Now that won't always be the case. In fact, this is a very unique example, which kind of leads us into the next thing. Gotta skip ahead, come back here. No, let's skip ahead here. Here we go. Which is the idea of independent events. Okay. So if that conditional probability of an event is the same as the unconditional probability, we say these two events are independent. It doesn't matter that I know that A has occurred. It doesn't change the probability that I see B occur. This might be something like, you know, I guess you could argue this isn't true, but if I tell you that, what's the probability somebody makes over $100,000? There's some number that is, right? But then it's okay. Given that they're over 6 foot tall, what's the probability that they make over $100,000? Well, height really shouldn't be related to income in any major way. And so, maybe we need to exclude basketball or professional sports players and make sure we're not taking any of that. But in the general public, right, your height isn't going to be related to your career income earnings, right? So it doesn't matter that I have this additional piece of information, underlying probability that event doesn't change, right? So that's the idea of independent events. So we'll come back to this in a second. So I threw up a slide here that just kind of has a nice summary of all those rules. So we talked about the complement rule, the addition rule, and now we've got this multiplication rule. Now the multiplication rule, we can kind of have two forms of it. All we're doing here is rearranging the equation. Sometimes we'll know the conditional probability and we want to solve for what the intersection is. Other times we know what the intersection is and we'll have to solve for what the conditional probability is. So it just kind of depends on the problem that we have. The initial ones that we'll be looking at, we'll be solving for what the conditional probability is, right? If you think about a contingency table, I don't have a conditional probability anywhere here. All I know are the probability of the intersections of those events. Now, next week, we'll talk about something called Bayes' theorem. There, we usually know conditional probabilities, and we have to solve for the intersections, okay? But for today, right? How would I find the probability of R1 given C2, okay? So I don't think I gave you any problems on the Connect assignment like this, but in reality, you could do something a little bit different. So I'm not calling these A complement and B complement here. I'm just kind of saying C1 and C2. You actually could have a contingency table that has like 6 or 7 columns. So the example I would give is instead of saying what's the probability somebody makes over 100,000 and what's the probability somebody makes 100,000 or less, I just create more bins, right? So maybe I create 4. I say what's the probability they make between 0 and 50, 50 and 100, 100 and 150, above 150. So I still make sure that they like include every possible income, but I could just create more events there if I wanted to, right? I'm not going to push you guys to do that, but that in practice, these joint probability tables, is anybody? Probably not. No one's actuarial science, right? I don't think they have, it's only the graduate degree here. But that's essentially what actuaries do, right? They might have like huge contingency tables that like have different combinations of these different events, right? Because they're not just concerned with 2 events, they're going to have like every single age as an event, right? And then some, whatever risk factors that people in. Anyways, I digress. So if I wanted to use a contingency table to solve for a conditional probability. Okay. So I've got what? R1 given C2. The general form, if I go back, I was saying was, well, if I want a conditional probability, I'm going to take the intersection of those two events and divide by whatever I'm conditioning on. So what I'm conditioning on gives me my new space, right? My new denominator. So here, I could rewrite this as the intersection of these two events. And then I divide by, what am I conditioning on here? Yeah, what I'm conditioning on is what's on the right-hand side of that vertical line, right? So here, I divide by the probability of C2. Well, I can grab these values from the table, right? What's the intersection of R1 and C2? What's the probability of C2 occurring? Right? So I can come up with that conditional probability. Okay. What if I wanted? No. C2 given R2. What's my denominator going to be? R2. Yeah, I divide by the probability of whatever I'm conditioning on, which is what? 0.4. And then the numerator is, well, of that remaining space of R2, of that remaining space of 0.4, how much of it is in C2? Well, of the remaining space of R2, how much of it is in C2? 0.3, right? Or the intersection of those two events, 0.3 over 0.4, I get a conditional probability of 0.75. So another way of thinking about conditional probabilities from this contingency table, once you give me the event has occurred, once I know R2 has occurred, sorry, not the slide, the additional example I gave here, right? If I know that R2 has occurred, my remaining space is 0.4. Of that remaining space, 0.1 of it is in C1, and 0.2 of it is in C2. So if, sorry, did I say point? I don't know if I said the number right. Of that remaining space of 0.4, 0.3 of it is still in C2. Right? So 0.3 out of 0.4 would be 0.75, right? Or 3/4. Any questions over kind of calculating these conditional probabilities? Or just questions outside of it? Pushing further, yeah.
What are your office hours again?
So I usually am there Monday, Wednesday, Thursday from 2 to 4. Right? If that doesn't work, send me an email. We can find another time. I'm generally like I was here almost all yesterday. I'm just around the building a little bit more. So if there's a time that we can kind of schedule. Yeah. Any other questions? So I kind of already moved ahead talking about independent events. We said events are independent if the conditional probability of the event is the same as the unconditional, right? It doesn't matter that I have this additional piece of information that B has occurred, same probability that A occurs, right? These two things are, you gotta think about independence as like, they're not related. Okay? So we can basically come up with a nice check to see if things are independent. So we'll end up having 3 different ways of checking. We can check to see if either one of these holds, then we would say that A and B are independent events. But if 2 events are independent, we'll also know that this equation will hold. So why will this equation hold? Or sorry, I missed. I jumped ahead. So this equation will hold. But how do we get to that equation? Well, we start with our multiplication rule. If 2 events are independent, we know that the conditional probability of B is the same as the unconditional probability of B. So if they are independent, I should be able to substitute in here just the probability of B. Right? If I do that, I've got my third way of checking for independence, which is if the intersection of 2 events is simply the probability of each event multiplied by each other, I know they're independent. Okay. So I'll kind of show you how we would check this on the contingency table. Okay. So this is kind of our third way of checking for independence. We can do it either one of these, and they'll all show us that these two events are either independent or they're not, right? If, you know, if A is independent from B, B is independent from A. So, here we go. How do we check that? So we'll use a contingency table. The first way, we'll just say, well, let's just use the actual definition of what independence is. That the conditional and unconditional probability of an event are the same thing. So here, I'll check the first one, right? So what's the probability? We've got the probability of A should be the same as the probability of A given B. Well, I can rewrite that conditional probability, right? I know it's just the intersection of those two events divided by whatever I'm conditioning on. Here I'm conditioning on event B. So all I do here is plug in the values from my contingency table. If this equality holds, I say they are independent. If it doesn't hold, then they're not independent events. So here we can check to see if this is true. So what's the probability of A here? 0.15. So I want just the probability of A. I would go all the way over to the total column, right? So that probability of just A, 0.6. What's the probability of A and B? Well, that is those top four left cells. That was the 0.15. Yep. So the intersection here is 0.15. What's the probability of just event B occurring? Yeah, it goes down to that total column underneath that event B. 0.25. Check this out in your calculator. Sure enough, that equality holds, and we would say these are independent events. Yeah. We could also check the other way, or check it another way. So here, I check to see if the unconditional and the conditional probability of A were equal. Now I'm going to check to see if the unconditional and the conditional probability of B are equal, right? Well, once again, I have to rewrite my conditional probability because that value isn't in my table, right? So I'll take the intersection of those two events and then divide by whatever I'm conditioning on. So what's the probability of B? 0.25 here on that one. What's the probability of B and A? Yeah.
0.85.
Point what?
85.
So it would be 0.85, right? These should all be values that we can get from the table, right? This is where we said order doesn't matter, right? If I want the probability of A and B, that's, oh, I wrote this. No, I wrote this right, sorry. If I want the probability of A and B, that's the same as the probability of B and A, right? This intersection represents, or sorry, this contingency table, these top four left cells represent the intersections of the row and column headings. So the intersection of events A and B, or if I say it the other way, the intersections of B and A, it's talking about the same thing. This should also be 0.15.
So it's the same throughout the whole country.
It happens to be the same here because we're really talking about the same thing. Remember, if we go back, we said the order doesn't matter. Doesn't matter if I say the probability of A and B or the probability of B and A. But then I have one more component, which what is the probability of A? Go over to the total column, just 0.6. If I put this into my calculator, sure enough, I see that if I check it this way as well, I end up seeing that the equality holds and they are independent. So it doesn't matter which conditional and unconditional probability I'm looking at, like as long as it's for the same event, right? Unconditional, conditional probability of A, unconditional, conditional probability of B. If I use either one of those to check it, they should both tell me that they're independent. The equality should hold under both situations.
I was gonna say, so it'd probably be a lot easier to like, when we're doing this, to put what each one would total out to, so like A and B for each one, like different, for like, if we had to make the chart.
If you have to make that chart at the bottom,
Yeah, like. I was just saying it'd probably be better to like label them, like, this would be A and B, this totaled out, like, you know what I mean, or this would be.
they told them out. So you're talking about when we're writing the equations out?
Yeah, like what each one would equal to, like at the end or the sides.
Yeah, I mean, I'm writing it out even more so than I have to. Like, if you have the formula in front of you and you see like, oh, this is how I check independence.
Mhm.
Yeah, you could just write the numbers in there. I just think it helps to kind of have, just writing it out so we can kind of see what the intermediate steps are. So like here, right, I kind of have what that conditional probability is. I just rewrote it. Because I can't get the conditional probability directly from this table. But the two components that I know that I can use to calculate that conditional probability, well, intersections are these top 4 left cells, so that's in my table, and then the probability of the events themselves. I don't know if I'm answering the question 100%.
No, yeah.
So I can plug those values in, see what those qualities hold, just like we did up here. The third way to check, and I think is probably the easiest, is I said, we go back. If they're independent, I can know that my multiplication rule, I can rewrite my conditional probability as just the unconditional probability. So that the intersection of the two events should just be the probability of each event multiplied by each other. So in this case, if I were to erase this. So really what I'm saying is the probability of A and B, if they're independent, should be the same as the probability of A times the probability of B. Well, I can check that with my contingency table. I think I have it right here. So what's the probability of the intersection of A and B? Use this a couple times now. Yeah, just that 0.15. What's the probability of A? 0.6. Probability of B is. If I enter this in my calculator, what I end up finding out is, sure enough, the equality holds for this third way to check for independence. I think this way is easier because you don't have to worry about rewriting conditional probabilities. You can literally just, well, what's the intersection of the two events? What are the probability of the events themselves, right? And if this holds, they're independent. If it doesn't hold, we would say they're not independent, right? If, for whatever reason, this isn't the case in this situation, but let's say, I don't know, I end up finding out that if I multiply the probability of A and B, I end up getting 0.4, so these aren't equal. Well, there we would say kind of they're not independent or that they are dependent, right? That knowing that B has occurred actually changed the probability of A. So we can grab those values and kind of check that out. Any other questions? I think, I don't know if we'll start it today. I think the example that we'll definitely complete on Monday, using some actual Excel data and like putting some names to these events, which will maybe help think about what these conditional probabilities are telling us and why the way we calculate that actually gives some kind of useful information. For now, we can have just the definitions and kind of try to understand the mathematics a little bit behind. Now, I'm not going to expect you to necessarily know this, but it's an interesting kind of byproduct. And I can give you an example, but I'll show you the equation first and just kind of. So if you have two events that are independent, A is independent from B, what ends up actually being true is that the complements end up being independent as well. So we can actually check this on the contingency table to see if that holds, because we've already proven that A and B are independent. And I'm telling you, well, if they are independent, their complements should be as well. Well, if the complements were independent, then the intersection of the complements should just be the product of, or the probability of each complement multiplied by each other. So here, what's the intersection of the complements? Probability of A complement and B complement occurring is 0.3. What's the probability of A complement? 0.4. Probability of B complement 0.75. We plug those in. Sure enough, 0.4 times 0.75 is the same as that intersection of the complement. So two events are independent. Their complements are as well. So how does this make sense? Well, we think about my example of income and height. if I tell you that, you know, those are independent events, right? That given that I know someone's over 6 foot tall, it doesn't change the probability of them making over $100,000. Well, then B complement, knowing that they're under 6 foot tall, shouldn't change the probability of A complement that they make less than $100,000, right? If those two things aren't related, right, they're independent from each other, and their complements will end up being independent as well. But like I said, I'm not necessarily expect you to kind of know or kind of use the fact that these complements are dependent. It's kind of a unique thing that kind of comes out of it. So this is kind of, I'll start maybe do some interesting probability along the way. Maybe convince or trick people, I guess, into thinking that you're clever. So what's kind of interesting is if events are independent, we can get some kind of weird things, especially when we're thinking about like rolling a dice. So if I'm rolling a dice, right, what's the probability that I roll a 3 with one roll? 1 out of 6, right? But what's the probability that I get a combination of 3, right? Well, there's really 2 ways to do it, but I'll show you the one and it would hold for the other one as well. So really what I'm saying is what's the probability that I get, what do I want to call this? Roll 1, I see a 1, and roll 2, I see a 2, right? That way the sum of my 2 rolls add up to 3, right? So the probability that if I roll a dice twice that I get a 3, well, there's a 1/6 chance that I roll a 1 on the first roll. There's a 1/6 chance I roll a 2 on the second. If each roll is independent, right? It doesn't matter what I rolled the first time. It doesn't impact the probability of what I get the second roll, right? Then it should be that this is just the probability that I get a 1 on the first roll times the probability that I get a 2 on the second roll. If each of these are 1/6, 1/6 times 1/6 gives me that 1/36, right? So it's actually way less likely that I actually roll a total of 3 between 2 rolls than I roll a 3 with just 1 roll. And it really comes from the fact that these are kind of independent events. Another way of thinking about independent events, and this holding out, I'm gonna use this one earlier, so I think I like this. So before we kind of use the independence, if I'm flipping a coin twice, what are the possible outcomes? I think I used this last class, but you can see a heads and a heads, tails and then a tails, heads then a tails, or tails then a heads, right? So I've really got 4 possible outcomes. So intuitively here, what's the probability that I get 2 heads in a row? That's 4 possible outcomes, so 0.25. Right? But you could actually do this with any number of coin flips you want, right? Because coin flips are independent events. If I flip a coin, it comes up heads 5 times in a row. On that 6th flip, what's the probability I get a heads? Still 0.5. Doesn't matter what happened on the previous 5 flips, right? Unless I've got like a weighted coin, but we're assuming we have a fair coin here. So, anything about here, what's the probability flip 1 comes up heads and flip 2 comes up heads? Well, if these are independent events, it should be that the intersection of those 2 events is just equal to, what do I call this, flip 1, so F1. Should be just the probability of each event multiplied by each other to get that intersection. Well, sure enough, what's the probability I get a heads in the first flip? What's the probability I get a heads in the second? So the probability that I get a heads on both is 1/4. Now, intuitively, we kind of do that with just 2 coin flips. It's kind of easy. But if we want to know what's the probability I get 10 in a row, well, the probability I get a heads in the first flip and a heads in the second and a heads in the third and a heads in the fourth, it would just be take the probability that I get a heads on the first times the probability I heads in the second, so on and so forth, right? So really all I'm doing there is saying take 0.5 and raise it to whatever number of flips I'm interested in. So this will kind of help us out once we get to talking about independent events, we'll start to talk about discrete distributions. This is a little bit down the road, but this kind of idea will help us out. So I think here, I'll at least start what we're gonna pick up on Monday. So any questions related to this independent stuff before we kind of see how do we actually build our own contingency tables with actual data? So I put a file up on Canvas, and really this is going to get us kind of set up for next class. So under the Files tab, we'll go to in-class data. I've got this county COVID data. So I had this idea. I honestly don't know what it's going to show. So we're in this together. But I had a bunch of data from last fall on different counties, their vaccination percentages, cases per person, all this stuff. I actually think it's a little bit more of an interesting question for kind of like individual behavior, that we're going to look at the relationship, maybe dependence or independence, of the median income in a county and then the corresponding percent of people that got vaccinated in that county, right? To see that if we know something about income in a county, could we actually, we have a different probability that they had a higher percent vaccinated. So I've got all these variables. So one thing, just kind of showing you some tricks in Excel. I'm going to select this entire data set very quickly. So I'm going to go to this very first cell, Control Shift or Command Shift on a Mac, hit the over, then the down arrow. Okay. I'm then just going to right click, copy this. I could use my shortcuts as well if I wanted to. And then I'm going to paste, right? So when I paste things in Excel, a lot of the times you'll want to do this, especially if you're just pasting the data. I just want to paste the values. So there's a bunch of different options, right? Maybe I want formulas to copy over. Here, I'm just pasting values. So I'm going to paste those values. Okay. I then want to only keep this column Q and this column N, right? My median household income and my percent vaccinated. And just for the sake of it, so we can see what these counties are and what states, I'm going to keep those two as well. So an easy way to quickly delete variables that you don't want to use, well, first of all, a good data practice is keep the original data intact, right? I'm copying and pasting this on a different sheet in Excel so that I'm not messing with the original data here, right? I just want to make it easier to work with, and I know I'm only going to work with two variables for right now. So if I go up to these column headings and I left click and kind of drag, I can select multiple columns at once. Now, if I just hit delete, notice it gets rid of all of that data, right? But I don't really want these blank columns, right? So if I undo that and I select them again, if I right click and then go to the delete option, this will get rid of the columns altogether. Okay, so that's kind of nice, kind of handy that way. I don't have to do it in 2 seconds. Just right click, delete. So I said I'm going to keep the county names. I'm then going to, once again, click and drag over up to the household income. I want to get rid of all of these. So I'm going to delete these. And then I don't really want these either. And the cases per person are here. I'm going to get rid of that. Okay. So it just makes it easier to work with. I don't know. Also, once I zoom in, it's going to be a lot easier to have fewer variables so you guys can kind of see what I'm doing. Okay. So the first thing we're going to do is think about, so I'll do income, just call this vaccinated. I just want to find the means just to get an idea about where the middle of kind of these variables are. So I'm going to use that average function. I'm then going to go over to that household income, select the entire variable. And I've got the average income across these counties is about 55,000. I then want to say, okay, what percent of your populace being vaccinated, what's the average there? So I'll select that variable. Once again, Control Shift, Command Shift on a Mac, hit the down arrow. Now I've got my two means. So I'm going to set this up initially to just think about counties that have high income will be those that have above average income. And I'll think about counties that have a high percent vaccinated above average. Okay. So I'm going to set up my contingency table. I'm going to have my events A complement, and my events B and B complement. Okay. My event A is above average income. And then the complement of that would be average income or what? Oh, if I can spell. Oh, geez, come on. Okay. Average income or below. Now I could write this out kind of mathematically, right? I could write like greater than the mean and then less than or equal to the mean. But here I want to kind of have some words. So we got this nice visual that even if someone not from a stats class was looking at this, they kind of eventually at the very end will understand what we're looking at. Okay. My other event is going to be, well, did these counties have above average vaccinated percents? I'm just going to kind of shorthand that for us. And then the other would be, did they have the average vaccinated percent or below, right? So I know that every county will have to fit somewhere in there, right? They either had above average or they had the average or below. Okay. So these are my events. I'm then going to want to use my count ifs formula to figure out the number of counties that had above average income, but also above the average vaccination, right? Or above average vaccination percent. Okay. Remember, that's that count ifs can do that for me. It can go through the data, count the observation if the income is greater than the average, and then go back through the data again and only count it if it also has above average vaccination percentage. Once I have these frequencies, how could I turn them into probabilities? Because we're eventually going to want our own contingency table, our joint probability table. So if I had frequencies, let's say, do we remember how could I find the sample size of this data pretty quickly? Do you remember what function we had there? Yeah, just that count function. So I'm just going to go over, count the number of cells that just had information in it. So I've got 3,000, a little more than 3,000 counties. So let's say I use that count ifs and I end up finding that 1,000 of the counties have above average income and above average vaccination percent. How could I quickly turn that into a probability? Yeah, it's 1,000 out of 3,100, right? So just take that frequency, divide it by the total number of counties or the total number of observations I have here. So once I get these frequencies, I can then turn them into probabilities. Now I've got my joint probability or my contingency table, and I can start asking questions like, are these two events independent, right? Or, what's the probability I see a county have above average income and above average vaccination percent? And then I'll eventually show you that we don't even have to use the averages. We could start to play around with the values. And if we reference everything correctly, we can very quickly update our joint probability tables, okay? All right, so I'm gonna save this and then we're gonna start back with this on Monday. In the meantime, like I said, you should see that after today's due date for that first homework. The next Connect assignment will pop up. I would start kind of working on those early problems because we've already covered a decent amount of those first few problems that'll be on that next homework, okay? Yep. Yep. All right. I'll see you guys. Have a good, safe, fun weekend, and I'll see you on Monday. Yeah, here.